Taking the derivative of a function and rotating a 3D vector follow the exact same mathematical rules. They are both linear operators, the bridge connecting standard linear algebra to the differential equations of physics. These operators exist within a specific mathematical environment. We build them on vector spaces, where we can add elements and scale them, and apply them in normed spaces, where we can measure the precise length of those elements. This 2D grid shows a linear transformation in action. As the space stretches and rotates, the parallel lines remain parallel, and the spacing remains consistent. The operator transforms the space while preserving its structural grid. This preservation follows a strict rule. T of alpha x plus beta y equals alpha tx plus beta ty. You can scale two vectors and add them, then apply the transformation, or you can transform them first and add them after. The final coordinates are identical. Because of this rule, inputting the zero vector must output the zero vector. If an operator shifts the origin point, the grid breaks, and the mapping becomes a chaotic transformation instead of a linear one. This diagram shows how operators move data. On the left is the domain, representing all our valid inputs. The arrows point to the codomain on the right, which represents all possible destinations. Notice the operator lands in a smaller subset inside that destination. That specific landing zone is the range. Within the domain, there is a specific set of vectors that map directly to the zero coordinate. We call this set the kernel, or null space. In finite dimensions, the identity operator maps every vector to itself, while the zero operator maps everything to the origin. Standard matrices use these same rules, using dot products to project vectors or cross products to rotate them. Every matrix is a linear operator, but matrices are confined to finite dimensions. To solve more complex problems, we must apply these same rules to infinite dimensional spaces. Here, a sine wave acts as our input. When we define the operator as t of x equals x prime, the sine wave transforms into its derivative, a cosine wave. Differentiation acts as a linear operator mapping elements across an infinite dimensional space of functions. Schrödinger used these functional mappings to build his wave equation, treating physical observables like position and momentum as operators acting on wave functions to calculate atomic energy. On top, two wave functions add together cleanly, preserving their shapes through superposition. Below, the function is squared. Squaring distorts the wave geometry. We rely on linearity so we can break down complex waves, process them individually, and perfectly recombine them. These rules prove that the kernel is a closed vector subspace. If you take two different elements that both map to zero and add them together, their combined sum will still map directly to zero. If the kernel contains any element other than zero, the operator takes distinct inputs and merges them into the same output. Once those points are merged, you cannot pull them apart to map them backward. The information is lost. This shows that an operator can only be reversed if its null space is zero, ensuring no data is merged. For a true inverse, we also require the range to date every point in the destination space. Only this combination allows us to move back and forth between spaces without losing information. Let's test this logic. If an inverse operator exists, prove that it must be linear. Try to show that T inverse of y1 plus y2 equals T inverse of y1 plus T inverse of y2. You have 5 seconds. Since T is linear, T applied to the sum of T inverse y1 and T inverse y2 equals T of T inverse y. The T and T inverses cancel, leaving y1 plus y2. By applying T inverse to both sides, the linearity of the inverse is confirmed. To summarize, we define a linear operator by its preservation of addition and scaling. We map it through the domain, range, and kernel. We extend it to infinite spaces through derivatives and integrals, and we check the null space and range to determine if the transformation can be reversed. If you want complete explanations of books like Kreyszig, Rudin, Functional Analysis, Linear Algebra, Real Analysis, and Topology, then don't forget to like, subscribe, and share this video. Comment below which theorem, proof, or chapter you want explained next.